Hello everyone, and welcome to my presentation. I am Tolga Türker, and I'm a graduate student at Computer Engineering Department in Aeronautics and Space Technologies Institute in Turkish Air Force Academy. And today I'm going to talk about the flight route planning problem for multiple unmanned aerial vehicle systems, and I'll introduce you a parallel simulated annealing method, which we have implemented it on graphics processing units or GPUs using NVIDIA's parallel computing platform CUDA in order to speed up the competition process. So before going to my main presentation, I would like to introduce the contents of it. First, I will talk about the objective of our study, and I'll try to give you a brief introduction about our study. And then I will give you some background information about simulated annealing optimization technique and NVIDIA's Compute Unified Device Architecture technology, which is also called as CUDA. After that, I will talk about the implementation details of parallel simulated annealing algorithm we use in this study. Then, at the end of the presentation, uh, simulation results and conclusion parts will be our subject. So, what is our objective in this study? The purpose of this research is to provide an efficient GPU-accelerated way to compute near-optimal flight routes for single-depot multi-UAV systems. Generally, in practice, if the system is composed of homogeneous UAVs, flight routes for each UAV are required to be as close as possible to each other in terms of travel distance. So this requirement is also considered as a constraint in the study, and because it is not feasible to use exact search algorithms because of the computational complexity of the route planning problem, simulated annealing algorithm, which is a probabilistic local search technique, is preferred to use in this study. As you probably all know that recent advances in aeronautic, electronic and communication technologies have enabled the usage of unmanned aerial vehicles or UAVs in different application areas. Uh, Traditional or single UAV systems, which have been used in practice for decades, are composed of large, expensive, and powerful UAV. On the other hand, multi-UAV systems consist of a group of small, low-cost, and mostly autonomous UAVs working together, especially in collaboration with each other. In a typical aerial surveillance mission, a number of predefined geographical locations, which is also called as waypoints, need to be traversed in a certain order by a UAV. And the order of these waypoints, which the UAV should follow, is called as flight route. In order to minimize the energy consumption of the UAV, it is necessary to find the optimal flight route which provides the minimum total travel distance. However, for a large number of waypoints to be visited, uh, searching for the optimal flight route with deterministic methods, it requires an excessive amount of computational time because of combinatorial nature of the problem. Additionally, in the case of planning routes for a multi-UAV system, there are some additional parameters to be considered, such as the number of UAV in the system, or takeoff and landing points of each UAV, etc. Clearly, using multiple UAVs complicates the route planning problem further and necessitates a lot more computation time to obtain the optimal flight route. So, the competition of optimal route for these surveillance missions is the main challenging issue in the flight route planning process, and it requires some special optimization methods in practice. Simulated annealing is a stochastic local search algorithm which is able to escape from local optima by allowing some worsening moves probabilistically. Um, as it can be inferred from its name, simulated annealing is built on the basis of annealing in solids. In physical context, annealing is a process of increasing the temperature of the heat bath for a solid until it melts, and then lowering the temperature sufficiently low in order to obtain perfect structural integrity for this solid, which is also called the ground state. Uh, so uh, however, reaching this ground state is not very simple. It is required to increase the temperature sufficiently high and also decrease it sufficiently slow. Otherwise, metastable states can be obtained, or a process called quenching may be observed. So basically, this algorithm provides a framework for optimization of complex systems through the analogy between this physical phenomenon and optimization problems. The most important algorithmic feature of this algorithm is its capability of escaping from local optima by using the metropolis acceptance function, as you can see from the screen. So, what is CUDA? CUDA is introduced by NVIDIA in 2006 as a general-purpose parallel computing programming model and architecture. And this technology provides significant increases in computing performance owing to parallel compute mechanism of NVIDIA GPUs. Here I want to note that many-thread GPUs and general-purpose multi-core CPUs have different design principles. I mean, they have different design philosophies. CPUs are designed with the intent of providing minimum execution latency for a single thread, but GPUs are designed as throughput-oriented devices which maximize the total execution throughput of a large number of threads. So, GPUs cannot perform well on tasks demanding one or very few threads, which are more sensible to perform on CPUs. It is therefore important for a program to be executed on both CPU and GPU for better resource utilization. So in order to address this need, CUDA provides heterogeneous execution model, as you can see from the screen, which enables the execution of compute-intensive parts on GPU and sequential parts on CPU. In CUDA programming model, threads are grouped into blocks and blocks are grouped into a grid, as you can see from the device architecture uh, figure on the screen. Uh, and CUDA has additional techniques to access memory, which can reduce the amount of data requests to the global memory in order to prevent the access traffic congestion. Global and constant memories can be accessed by the host using CUDA API functions. Also, these two memory types can be accessed by all threads in the system during the execution. Global memory, as I mentioned before, is typically dynamic random access memory and tends to have a long access latencies. On the other hand, the constant memory provides shorter latency, read-only access by the device for the cases when all threads want to access to the same location. In addition to these two off-chip memories, registers and shared memory provides very high-speed access. Registers are used by individual threads for keeping frequently accessed variables and can be accessed by only associated thread. And finally, shared memory is used by thread blocks for thread cooperation and sharing. So, in order to develop high-performance parallel applications, it is important to optimize the kernel's memory access model, as you can see. So, let's look at the implementation details of our GPU-based parallel simulated annealing algorithm. In this study, we have used multi-chromosome genetic representation technique to represent solutions in our algorithm. And here in the figure, uh, it illustrates this representation for 11 waypoints and 3 UAVs, as you can see. Node H in the graph shows the home, which represents the single takeoff and landing point for all UAVs in the system. and it is therefore important to note that the numbers 0, 1, and 2 is used in the solution are reserved for 3 UAVs in the system, and each of them indicates the same type of landing point. So as you can see, there are three individual routes, the yellow one and green one and the blue one, and each UAV take off the same home points and then traverse its points, its corresponding points, and then returns back to the home point again. So our solution is formed by individual routes. These individual routes for each UAV, as it is illustrated by merging route 0, route 1, and route 2. So, each element in the solution denotes a geographical position to be visited for UAVs. As I mentioned earlier, in addition to try to find the route with minimum total travel cost, we also want to make each individual route to have close cost values as much as possible. In this context, we set our initial solution using a simple heuristic. It is clear that if the points representing the takeoff and the landing points of UAVs are located into the indices which are too close to each other in the solution vector, then it is quite not possible to start with a solution with better cost value. So in this context, we organize the initial solution by locating each takeoff point for UVs equidistantly in the solution vector. With this way, we are hoping to have a solution with better quality. And normally, searching for the best route for a UAV typically means searching the shortest route. But for a multi-UAV system, total travel cost is considered as to be the minimum. In addition to that, this study is looking for fair route distribution in terms of individual route costs of UAVs. I mean, our study does not focus only to minimize the total travel cost for the multi-UAV system. Individual flight routes for UAVs in the system are also considered to be as close as possible to each other in terms of individual route costs. So, in order to ensure this additional requirement, we have used a penalty-based approach. The, the difference between the individual flight routes with minimum cost and the maximum cost, which we can say Cmax and Cme, is added to the CT, which means the total travel cost. With this way, a greater difference between the minimum and maximum individual routes cause a worsened solution with its greater penalty. So these routes will be less preferable by the algorithm. So simulated annealing algorithm can be implemented using two different approaches, the homogeneous and the inhomogeneous versions. In this study, homogeneous version is used due to its capability over controlling the equilibrium state. The implementation of parallel simulated annealing algorithm for route planning consists of two major nested loops as it is presented in the figure. And these are cooling loop, which controls the temperature of the system, and the equilibrium state loop, which all threads in the GPU are responsible to execute it as a CUDA kernel to reach the equilibrium state. So the cooling loop, as being the outer loop of the algorithm, is controlled by the host using static geometric cooling schedule. In each iteration, the temperature as the main control parameter of the algorithm is increased by multiplying a predefined cooling factor. In addition to cooling scheduling, this loop is also responsible for selection of the best solution within the solutions found and returned by all CUDA threads. The best solution is cloned into an array with size of number of threads in order to comply with data parallel competition mechanism of CUDA. This is because all CUDA threads should perform their competition on their own data portion to exploit the data parallelism. Then this solution array, which is composed of the same best solutions and decreased temperature, are sent to device global memory, I mean GPU DRAM, by passing them as CUDA kernel parameters, as you can see in the view. For each iteration of cooling loop, these operations are repeated until reaching the defined stopping criteria. So these algorithms are implemented both on CPU and GPU for performance comparisons, and you can see the hardware specifications in the table below. We have used GeForce 840M, which is a kind of end-user graphics card of NVIDIA, and the initial temperature of our algorithm is selected as 40 because of its average initial acceptance percentage, which is actually 60%, and cooling iteration is set to 1000, and all GPU tests are executed with 128 threads. And in addition to that, the equilibrium state duration, which each thread executes, is set to 10 for all tests. So the multi-UAV system is considered as consisting 3 UAVs, as you can see, and datasets with 52, 100, and 225 waypoints are used in our experiments. And now you're seeing the experiment result for 52 waypoints and, as I mentioned, 3 UAVs. As it is presented, a GPU implementation provides better total travel cost values for the similar number of iterations. As you can see here, the cooling iteration, and here and on y-axis the total root costs, and the red line indicates the GPU's results, and the blue one indicates CPU results. And as you can see here, for the same iteration, the GPU finds better total root cause for the same cooling iteration. So here you can see the simulation results for datasets with 100 and 225 waypoints. Here you can see the results for 100 waypoints, and this one is for 225 points. And again, it can be inferred from the figures here. As the number of waypoints increases, the difference between the total travel costs provided by CPU and GPU at a certain iteration also increases at the beginning of the iterations. It is therefore important to note that GPU implementation of simulated annealing algorithm provides better solutions as compared to serial CPU implementation. So, as a result, experiments shows the efficiency of GPU implementation of simulated annealing algorithm. So, as a result, with this study, we present an alternative way to compute cost-fair flight routes for single-station multi-UAV systems efficiently, and a simulated annealing algorithm is used to deal with exponentially increasing competition time of route planning problem because of its combinatorial nature. And we have redesigned the algorithm by making some modifications for GPU acceleration, and we have implemented it using CUDA platform in order to exploit data parallel compute mechanism of NVIDIA GPUs. And experimental results show that GPU accelerated simulated annealing algorithm provides significant increases in computing performance for flight route planning problem. So, thank you for listening to me. And if you have any questions, um, you can send an email to the addresses below. Thank you.